Hello again, Physics 20s. In today's lesson, we are going to discuss a phenomenon that is referred to as mechanical resonance, and then we are going to apply mechanical resonance both to structures and to the operation of simple musical instruments. Learning outcomes are to 1, define mechanical resonance, and 2, explain qualitatively the conditions for constructive and destructive interference of waves and for acoustic resonance. However, before we can talk about what mechanical resonance is, we need to clarify what a standing wave is. A standing wave, to explain it properly, is best understood if we look at a picture that is not static. We need a dynamic kind of app to look at this to understand what's going on. So I'm just going to clarify a couple of notes here, and then I'll go to an animation where I show you how we can produce one of these and describe what a standing wave is. So a standing wave is a condition in a medium where a wave seems to oscillate about stationary points that are called nodes. Okay, we'll come back to that point in a moment. To produce a standing wave, you need to have two waves with the same amplitude and same wavelength traveling in opposite directions. And the interference of these two waves is then going to produce what we call a standing wave. Let's go to the app to look at this. Okay, so what I have here is I have a string that is fastened to a fixed boundary. And what I'm going to do is, let's say that someone just like flicks the string from the left-hand side, and we can start to see like the wave pulses that are being generated. And the particles in the medium are just vibrating up and down, up and down, up and down, as were the direction of wave propagation or energy transfers towards the right. So this would be an example of a transverse wave because the direction of wave propagation and particle vibration are perpendicular. Okay, when this wave is about to hit the wall or the fixed boundary, I'm just going to pause it for a brief moment. Okay, so pause it right here. Okay, so this red wave is what we're going to call the incident wave. So the incident wave is coming from the left-hand side from some kind of an unknown source. And again, it could just be a person grabbing the string and just like pulling it up and down, up and down, up and down. We're going to see now a second wave that's going to be blue in color, and that's going to be the reflected wave as a result of this wave hitting that fixed boundary. Now, I'm just going to pause it briefly for a moment here. Let's get rid of this. Okay, so I have this red wave, and I have this blue one, and you'll notice that the blue one is inverted. And why is it inverted? Well, because the wave's hitting a fixed boundary. If you hit a fixed boundary, the wave would exert an upward force on the boundary. The boundary would exert an equal and opposite downward force on the wave, and it would cause it to get inverted. Okay, so now what I have is I have my incident wave with a particular wavelength and amplitude moving towards the right. And then I have this reflected wave that has the same amplitude, same wavelength that's moving towards the left. And that's going to be my condition necessary to produce a standing wave. I need two waves moving in the opposite direction with the same wavelength and same amplitude. And their interference will lead to a standing wave. Okay, now I'm going to click this other button here, and this is going to show me the superimposed wave. So the superimposed wave would just be illustrating the combined amplitudes of both these waves at given points in time. Okay, so let's look at this. Now I'm going to pause at a couple of points just to illustrate how the interference is working. So let's pause right here. Okay, at this point, these two waves, the incident and the reflected one, they are perfectly in phase. So the crest of one meets the crest of another, the trough of one meets the trough of another. If I have crest meets crest and trough meets trough, that is the condition for constructive interference. So these waves would constructively interfere to give me the black wave. The black wave is a superimposed one. So in this part here, if I have a crest meet a crest, I'm going to get a jumbo crest. And specifically, it's going to be double the amplitude of one of these individual waves. And then down here, I have a trough meeting a trough, so I'm going to get a jumbo trough. So a jumbo trough is going to have double the amplitude of the trough of one of these. Okay, so let's keep going. And then I'm just going to pause it at another point about right here. Okay, so at this point, these waves are now meeting out of phase. When these waves meet out of phase, that means the crest of one meets the trough of another, and for this brief moment in time, the wave actually cancels off. So you're back to just at the rest position for this quick instant. Now, to kind of clean this up, I'm just going to remove the instant wave and the reflected wave, because all we're really interested in is the superimposed waves. Let's get rid of these two. This pattern that you see on the screen here is what we refer to as a standing wave pattern. Now, the way the standing wave works is that along your objects, like your string right here, I have these stationary points that are called nodes. So I have one here, I have one here. They're all labeled with a capital N. Here, 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 and here. Okay, so there's points that are not vibrating at all. They're kind of fixed in place. It's like someone has grabbed the string and just holding it there. Halfway in between these nodes, we have an antinode where the particles in the string are vibrating continuously from a trough all the way to a crest and vice versa. I shouldn't say vice versa, but trough to a crest, crest to a trough. Maybe that is vice versa. Okay, the interesting thing about a standing wave is it doesn't seem like the wave is actually moving towards the left or towards the right. It just appears as though the wave is kind of just flipping back and forth vertically about this horizontal x-axis here. So this little pattern we have, where we have stationary points called nodes and I have the wave oscillating in between them from a crest to a trough, that is what we call a standing wave. Now let's go back to the notes and see if we can make more sense of this. Okay, so a standing wave is a condition in a medium where a wave seems to oscillate about stationary points called nodes. Well, yeah, we saw that, okay? So on my animation, I had these points on the wave, capital N, where it seemed like someone was just grabbing on the string and not letting it vibrate. So I have all these stationary points called nodes. Halfway in between those nodes, the wave continuously oscillates from a crest to a trough, or from a trough to a crest. To produce one of these waves, you need two waves with the same amplitude, same wavelength, moving in opposite directions, and it's their interference that results in the superimposed wave we call a standing wave. And again, just a quick point of reminder. So when you think of a node, you should think node is nothing in terms of amplification. So node is where you have no vibration, and an antinode would be a point where you have amplification. So you're getting like your maximum amplitude continuously switching between a jumbo crest and a jumbo trough. So antinodes are points of maximum vibration. If you're interested in playing around with the app, you can look at this website link here. Although the link might be a little bit outdated, so in which case I would just type into Google Walter Fent apps and look for the standing wave app. Okay, now we're ready to talk about this phenomenon that's referred to as mechanical resonance. Certain objects prefer to oscillate at a specific frequency that will produce a standing wave pattern. If you can find an external wave that has the same frequency as an object's natural frequency, you can cause vibrations in the object with larger amplitudes. Okay, let's make sense of all this text here. And I'm going to use an example of a wine glass for this. So in this illustration, it's actually a video, I have a wine glass. Okay, now this wine glass has something that we refer to as a natural frequency. In fact, all objects have a natural frequency. It's a frequency in which they would prefer to vibrate at. They just might need a little bit of help to do it. Okay, I'm going to make up a fake number for this. Let's say the natural frequency of this wine glass is 60 hertz. 60 hertz natural frequency. Behind this wine glass, we have a speaker. Now, what this speaker is going to do is it's going to produce an external wave in the form of a sound wave. So I have a sound wave. Now, if the wine glass has a natural frequency of 60 hertz, and let's say that I generate a sound wave that has the same frequency of that, it has a 60 hertz frequency. So if I send the sound wave through the frequency of 60 hertz that matches the natural frequency of the wine glass, this is going to result in the production of a standing wave in the wine glass. If you can produce a standing wave in an object, that is what we refer to as mechanical resonance. Okay, so let's look at this now. So I said certain objects prefer to oscillate at a specific frequency. They'll produce a standing wave pattern. And there are, so this wine glass actually has, there's multiple frequencies that it can vibrate at that'll produce a standing wave. If you can take another wave from an external source and you can get it to match the natural frequency of an object, you can cause vibrations in the object with larger amplitude. So this would be my definition of what mechanical resonance is. I'd say it's a condition that occurs when a wave with the same frequency as an object's natural frequency causes vibrations in the object with larger amplitudes, which is just a way of saying you're producing a standing wave in the object. Okay, let's look at what would happen if we actually do this, if we have a sound wave that matches the natural frequency of the glass. Okay, so I'm just going to play the video here. Okay, so I can see the way the glass is starting to vibrate. So it's starting to vibrate because like the particles in the glass are trying to vibrate like a standing wave. Now the issue is the glass is like pretty brittle. It can't handle deforming into the shape of a standing wave. So as it starts to vibrate more and more and more, and it gets closer and closer to exhibiting that nice standing wave pattern, it shatters because the glass can't stand being deformed like a standing wave. So this is actually not a good thing if we're talking about a wine glass, because we don't want the wine glass to shatter. So it's actually not a good thing to match the natural frequency of the wine glass, because then you'll create a standing wave in it, which will make huge amplitudes in the glass and cause it to shatter. Another example of this is, I'll show you a video in a moment, the collapse of the Tacoma Narrows Bridge. So in this particular situation, I'll just make up some fake numbers again, then we'll look at the actual video. Okay, so we'll say that the bridge it has a natural frequency. And again, I'll make up a fake number, 100 hertz. Now, what happened on this particular day is that it was windy, okay? So you have like particles in the air moving because of the wind. So we can think of the wind as being a type of mechanical wave. So I'll call it like quote unquote a wind wave or something. And on this day, the frequency of the wind from my external source just happened to match the natural frequency of the bridge. Well, what happens when this occurs? Mechanical resonance. What does mechanical resonance involve? The production of a standing wave in your object. This is bad. Okay, so let's look at an actual video of this. Okay, you can see the YouTube link up here to view the video, but let's take a look at if you can see the standing wave. Okay, so this is when the bridge opened. Everybody's happy. They're driving across the bridge, celebrating. Times are good. And they're continuing to drive. Okay. So now we're at this day where we had the wind matching the natural frequency of the bridge. And what happens now? Oh my goodness. It's weird. Like you can see like it's just oscillating down and up and down and up. It almost seems like the middle of the bridge is kind of like in a way a note, I suppose. And again, the sides are just oscillating up and down, up and down, up and down. Now, to keep in mind, this bridge is probably made of a lot of concrete, and concrete is very brittle. It's not supposed to deform. I'm actually surprised that the bridge hasn't failed already based on like what you're seeing here. Okay, and let's go to a different view. Let's speed this up. Yeah, here's where I feel like I can really see the standing wave pattern where like I'm oscillating between like a trough to a crest to a trough to a crest, etc. Okay, what's going on now? Yeah, the bridge is continuing to oscillate. Oh, there's a car on it. Yeah, continuing, you need that oscillation between like a crest and a trough, etc. And let's just speed this up a little bit. Oh, there's a car in the bridge. Bad day to go for a joyride, I guess. Okay, and eventually, like I said, this concrete can't handle being deformed. So, was it really an hour later? Yeah, it collapsed and it failed. Okay, so let's go back to the PowerPoint now. Okay, whatever, the wine glass. Now, so I did mechanical engineering. I mean, I never worked as a day's mechanical engineer in my life, but one of the courses we did in our 4th year of mechanical engineering dealt with acoustics and vibrations, because this is something that, like, when you're designing structures, you need to make sure it does not happen. So you want to design structures that there's no chance that like the natural frequency of that object can be met. Because if the natural frequency of that object can be met, then if it's an object like a wine glass or a bridge, which is brittle, then it will fail. Now, if you're starting to panic and you're like, well, wait a second, I have a natural frequency. So is there a chance I could walk outside and the wind could like match my natural frequency and cause me to start vibrating like a standing wave? Yeah, I don't think you need to worry about it. I'm not sure what your natural frequency is, but I think there's like pretty much a 0% chance that any external source could actually cause you to start vibrating like that. So I think you're safe. You don't need to worry about, yes, you deforming like a standing wave. Okay, now we're going to focus in this lesson specifically on the mechanical resonance in strings. So I think the scenario we'll look at is, so let's say we have a couple of fixed boundaries. So I have one boundary like this, and then I have another boundary like that. And we're going to put a string just from one end to the other. And we're going to look at the mechanical resonance in a string. Now, this isn't a huge deal for a string because strings can deform a little bit. Okay, so I would not be as concerned with a string undergoing mechanical resonance as I would compared to glass or concrete. It turns out a string can be vibrated at multiple specific resonance frequencies. Now, whenever we see that word a resonance frequency means it is a frequency that you can get an object to vibrate at that will produce a standing wave pattern. And it turns out for a string, there are multiple resonance frequencies. So I'm just going to go to another animation here for a moment. Okay, let's look at this one. We're just going to focus on this middle diagram here, the one that says like displacement of particles as my title. Okay, so we have my string and it's fixed from one side or node to the other side or node. And someone's just taking that string and they just pull it down and let go. So that string just starts to vibrate up and down, up and down, up and down about that anti-node point. Now, this is a standing wave, okay? Because you have two stationary points called nodes and you're vibrating from crest to trough in between them. So one of these resonance frequencies in this situation is a frequency of 172 hertz. But there are other resonance frequencies as well. 344 hertz can also give you another standing wave. It just looks a little bit different because now you have a different number of loops on the actual string, but it's still a standing wave because you have a stationary point, a node, 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 and you're oscillating between crest and trough between them. And I can look at another resonance frequency, so 515 hertz. So again, I've got a standing wave pattern, it's just I have more loops in the actual string. Okay, so let's go back here now. So a string can be vibrated at multiple resonance frequencies. And again, a resonance frequency produces a standing wave pattern. The lowest resonance frequency that you can vibrate to produce a standing wave is what we call the fundamental frequency. So the fundamental frequency is the lowest resonance frequency, or we can refer to it as being the first harmonic. Your other resonance frequencies are going to be whole number multiples of the fundamental one. Okay, so we can go back to this animation now and we can see this. Okay, so this is my fundamental frequency. This is the lowest frequency in which you can get the string to vibrate at in a standing wave type pattern. The second resonance frequency, or the second harmonic, would be a whole number multiple of this value, a whole number multiple of 172. So if you double that number, it should be 344, okay? So this standing wave pattern I see right here is what we call the second resonance frequency, or the second harmonic. And if I go to one higher, well, the third resonance frequency would just be 3 times the fundamental frequency. It's just always going to be a whole number, I shouldn't say a whole number, a natural number multiple of the fundamental one. Okay, so that would be 172 multiplied by 3. They say 515 right here. I suspect that this frequency is actually 170. It probably has some decimals to it. So that'd be 3 times that. And then your fourth resonance frequency, or fourth harmonic, you would have a standing wave pattern that then looks like this guy right here. Okay, so what else do we note? Yeah, the other resonance frequencies are whole number multiples of the fundamental one. And as you go to higher resonance frequencies, you still produce a standing wave. The standing wave just looks different. So what's changing is the number of loops in the standing wave. Okay, so that's increasing for higher resonance frequencies. So let's look at this. And by the way, again, here's a link to the app. This time around, I think it's called longitudinal waves, or standing longitudinal waves. Okay, let's kind of summarize what we just saw. Okay, so the fundamental frequency is the lowest frequency in which you can actually produce a standing wave. This would be it's also referred to as the first harmonic, and in the first harmonic we get one loop. The second resonance frequency would be twice the fundamental frequency, which gives you the second harmonic. The second harmonic has 2 loops. And you can see the pattern just keeps going. So the third resonance frequency, or the third harmonic, would have 3 loops. The fourth resonance frequency, or the fourth harmonic, would have 4 loops. Now, we're also going to look at a mathematical equation that's going to relate the wavelength of the wave compared to the actual length of the string. Okay, so let's get into the math behind this. So we have 2 equations that we can use to calculate both wavelength and wave speed. To calculate the wavelength lambda is equal to 2 times L divided by N, where N is 1, 2, 3, etc. The wave speed can be calculated by V is equal to the square root of FA divided by M over L. These are 2 equations that have boxed in numbers. You'll find them on the additional formula sheet, but not on the regular one. Now, we need to clarify what these variables stand for. L represents the length of the string, and the length of the string is in units of meters. M is the mass of the string in units of kilograms. FA represents the magnitude of the tension in the string, which needs to be in newtons. N is going to be a reference to the resonance frequency or harmonic of interest. So like if we're talking about the fundamental frequency, the first resonance frequency, N would be equal to 1. If we're talking about the fourth harmonic or fourth resonance frequency, then N would be equal to 4. Okay, let us go back for a second and see if we can play around with this wavelength equation. Okay, so my wavelength equation looked like lambda is equal to 2L divided by n. Okay, so what this equation can be used to do is it can tell me how many wavelengths can, I suppose, fit into a particular length of the string. Okay, so if we're looking at the fundamental frequency, that would be where n is equal to 1. So you'd have lambda would then be equal to 2L divided by 1. Let's manipulate for L. So L would be equal to lambda over 2. Now look at the illustration here. So this is the length of the string. How many wavelengths actually fit into this length? Well, if we start here and trace the wave through an entire wavelength, you'd have to go all the way over here to get it. So the wavelength that we actually have fitting into this length right here would just be lambda over 2. It's half the wavelength. You actually don't even need to, if you can draw the picture, you can actually figure out what the connection is between the wavelength and the length without using the equation. But if you prefer to use the equation, that's fine. Well, let's look and see what happens at the second resonance frequency. So the second resonance frequency, we'd have lambda is equal to 2L divided by n. This time around, n is equal to 2 because we're talking about the second resonance frequency. So this would then be lambda is equal to 2L over 2, which tells me that in the length of the string, we have one full wavelength that fits in. Well, one full wavelength that fits in that's vibrating would correspond with 2 loops. Okay, so the equation is valid. You might be wondering, why in this equation do you have m over L? Like, why the 2 fractions? Like, why not just write it as FA L over m square root is equal to V? Well, it turns out that this ratio, m over L, is what we refer to as the linear mass density. So I suppose there could be another variable that could be used to represent it, but that's the only reason why. If we actually put the L up there, then it wouldn't be as clear that that is a ratio that is identifying a specific quantity. And the linear mass density is just telling you like how much mass fits into a particular length of the string. So the higher the linear mass density, it just means that there's more mass within a meter length of your string that you're looking at. A third note. So in talking about vibrating strings, we can immediately apply this to how specific musical instruments work. And I'll use 2 examples. So the easiest one, I suppose, is a guitar string, and another one is a piano. Because I believe what happens in a piano is inside of a piano, you have like a bunch of strings that are cut to like very specific lengths. And then you have like these hammers when you hit the key, these hammers that just strike the string and it causes it to vibrate. Now, in terms of music, resonance is actually a really good thing because if you can get strings to vibrate at specific frequencies, specifically the resonance frequencies, you get these really, really nice sounds. These sounds where the string is vibrating at the resonance frequency is what we would refer to as a musical note. Now, in terms of how you can get different musical notes, it involves altering things like the mass of the string, the length, and the tension. So let's look at this. This is my universal wave equation, V equals F times lambda. If I manipulate the universal wave equation for F, I would have F is equal to V divided by the wavelength. Now, to calculate V is equal to the square root of FA divided by M over L. So one way we could alter the frequency, and we'll talk more about like pitch and how we interpret sound in the next lesson, but one way we could alter the resonance frequency produced by a musical instrument would be to change the wave speed. Well, how can we change the wave speed? A few things. You could take your string and you could tighten it. Okay, you can make it like more tight or less tight. And the other thing is you'd look at the mass density. So I've done a little bit of music. When I was growing up, I did piano lessons where I learned Royal Conservatory of Music up until about grade 7, and that was pretty much as I could tolerate at that point. Uh, I think when pianos go out of tune, I think the issue is that the tension is not tight enough. So like to put it back into tune, I believe you need to tighten it, and then it can get back to giving you those nice resonance frequency sounds. And I'm not sure if it's totally correct, but I think different keys are attached to different strings, and some of these strings might have varying mass densities to it. So varying mass density can affect the speed, and if you change the speed, you can affect the frequency. I'd say the big one though, and this goes for a guitar, is that the other way you can change the actual resonance frequency is you can alter the wavelength. Well, how can you alter the wavelength? Change the length of the string. For a guitar, I believe what you do is you take your finger and you hold your finger at different points on the string and then use your other fingers to kind of just strum the, I don't know if it's strum or like vibrate the string in between. So your hand on the guitar is intentionally changing the length of the string to give you different notes. For a piano, those strings are already cut to specific lengths. So once that hammer hits the string at a different length, it's set up to produce those different resonance frequencies. Okay. So I'd say it's the two big ways that you can actually like get the different resonance frequencies of the different musical notes is one, look at strings with different mass densities, and then two, alter the length of the string. We'll talk more about acoustic resonance in the next lesson. We'll get into discussion of uh, objects that don't require like don't have a string. We'll look at things that like you can actually have vibration of the air particles. All right, that's it for this lesson, and you can complete the assignment called Resonance in Strings. And again, in the next lesson, we'll talk a lot more about acoustic resonance.